Good afternoon to one and all present here. I am Professor Ganesh BB, Assistant Professor, Department of Mechanical Engineering, VVCE, Mysuru. I wholeheartedly welcome you all for this today's webinar on convective heat transfer through extended surface by an eminent personality, Dr. Kankan Kishore Patak, Assistant Professor, GIMT, Assam. Dr. Kankan Kishore Patak received his MTech and PhD degree in NERIST, Arunachal Pradesh, India. Presently, he is working as assistant professor in the Department of Mechanical Engineering, JIMT, Guwahati. He served as guest faculty in NIT, Arunachal Pradesh. His research areas are extended surface heat transfer, energy and exergy analysis in thermal systems, and also he has presented many international and national papers. And Dr. Patak received MHRD and GET fellowship for pursuing PhD and MTech in NERIST. On behalf of entire VVC family, I wholeheartedly welcome Dr. Kankan Patak for today's session. I request Dr. Kankan to take over the session. Over to you, sir.
Okay, thank you. Okay. So, thank you very much, Mr. Ganesh. And hello, everyone. First of all, I want to thank all the organizers of this webinar for giving me this opportunity and to take on this particular topic. And I welcome all of you to this session. Okay. And for today's topic is actually the convection heat transfer through extended surface or fins. So before going to the details of how actually convection or the extended surface working, before that I just want to give some basic information on the convection as well as the extended surface. Now in this lecture I will talk about how the different modes of convection heat transfer, that is natural, mixed, and the forced convection studies can be formulated for the fin array in computational fluid dynamics approach, and results of 2 case studies will also be discussed. Now, this is actually the modes of heat transfer, as you all have noticed this one. Now we all know about that there are 3 modes of heat transfer, that is convection, conduction, and radiation. Now in case of the conduction, there will be a physical contact between the substance. The heat transfer is generally transferred from one part of the body to another part of the body of a same substance, or from the one part of the body to the another part of the body in contact, physically in contact with it, without appreciable displacement of the molecules forming the substance. That is actually the conduction. Now radiation, generally in case of the radiation, the energy emitted by the matter in the form of the electromagnetic waves, as a result of which actually the electronic configuration of the atoms and the molecules have changed. So in heat transfer studies, we are actually considering about the thermal radiation part, and the internal energy of the object decreases when we are considering the radiation. Now this conduction and radiation part I am not discussing today. Today I am discussing only the convection part. Now in detail, the convection parts I will study from the next slide, and after that I will discussing about the various extended surface behavior and through the convection. Now here we can see this is actually the convection heat transfer. What is actually the convection heat transfer? So convection heat transfer is the heat transfer process that is occurring from a solid to a fluid when the fluid is in bulk motion, which distinguishes it from conduction. Now convection is composed of 2 modes. One is the diffusion, that is across the boundary of the solid and the fluid, and another is the advection, that is bulk motion of the fluid. Now you can see in this figure I am showing the flowing of a fluid over a heated flat plate. Now whenever the temperature of this is maintained at a very high temperature and the fluid is flowing over it, now heat is actually transferring from that body to the fluid. Now what happens at the vicinity of the solid surfaces, the velocity actually is 0 because of the no slip condition, and it is gradually increases in the subsequent layers, and the retardation effect is actually decreases whenever the fluid layers moving, that is away from the solid surfaces. So the region in which the velocity, because in this figure you can see the V infinity and the T infinity are the velocities, and the temperatures of the streamwise fluid. Now this V infinity, it is along the y direction. This is the velocity of the stream. Now it is 0 here, and it will increasing, and it attains the velocity of the V infinity. So in this region, or within the region in which the velocity increases from 0 to the V infinity, that region is generally shown by the velocity boundary layer, or it is also known as the hydrodynamic boundary layer. Now again, if you consider about the thermal boundary layer also simultaneously developed in a heat transfer problem or fluid dynamics problem, the thermal boundary layer is because of it is due to the temperature differences occur between the surface and the flowing fluid. Now you can see at the surface the temperature is very high. Now at the fluid the temperature of, because the T infinity is less than this, is why the temperature is gradually decreasing here. Now here we see that the heat is transferred from the solid surface to the fluid. That is why the wall temperature is more, and that's why it is gradually decreasing up to fluid. Now if T infinity is greater than the TW, that means the fluid pressure is more than the wall temperature. That is, it is transferred from the fluid to the solid wall, and inside actually the temperature profile will actually is minimized or minimum at the wall, and then it is gradually increasing. So this equation number 2, very common question, that is the equation number is because the Fourier of heat flux heat transfer part is equal to minus K del T del Y, where Kf is conductivity of the fluid. Where we can use this one, we can use this equation. The it is conducted from the solid surface to the fluid. Solid surface fluid from here, we can apply this equation, and whenever it is conducted is in this boundary that is actually conducted to the fluid that is outside the boundary layer. And now from the fluid, that means heat transfer in the fluid, that is actually shown by Newton's law of cooling. This is equation 2 is a Newton's law of cooling, and from that also this is heat flux. Actually, it is heat divided by per unit area, and that will actually proportional to the temperature. Because it extensively used. Okay. So now this H is generally the heat transfer coefficient. Now you can see in this figure, now the value of the H depends upon the certain factors. What are those factors? The first factor is the thermodynamic and the transport properties. The transport properties means viscosity, density, specificity, etc. And nature of the fluid. How actually the fluid is flow. Is it forced or is it necessarily occurring? Depending on that, the nature of fluid flow, heat transfer will be different, or it is depending. Now again, the geometry of the surface. Geometry of the surface means the area above which actually heat is transferred, and what type of cross-sectional area is exposed to the heat transfer. So that is geometry. Now preventing conditions generally depending on the various temperature difference, because the many cases the temperature difference is fixed. So depending on the difference of the temperatures, so may vary. Now heat transfer coefficient is a function of the length of the plate, but in general the average heat transfer coefficient is used to calculate the heat flux. The mean or average heat transfer coefficient for a surface that is determined by averaging the local heat transfer coefficient over the entire surface. Now convective heat transfer coefficient is related to thermal conductivity by Nonuniform number, that is given in the DP 2002. This is a book, Reynolds, and from there the Nonuniform number is written by. Actually, this is it is the convection in the presence of the conduction. It is a ratio of the heat transfer, convective heat transfer to the conductive heat transfer. Now the Nonuniform number also can be related to the fluid flow by Reynolds and the Prandtl number. Now, Reynolds number plays a vital role in case of the forced convection. The modes of the convection part I will describing next. But the basic thing, because for Nusselt number, whenever we are seeing about a convection, the Nusselt number, Prandtl number, Grashof number, these all equation, all the non-dimensional number plays a important role. For laminar flow, the correlation between Nusselt number and Reynolds number that can be given by this formula. This is for laminar flow. For turbulent, it is maybe different. Now, for validity of this equation is lies between when a Prandtl number is less than 0.6 and number is less than 5. That is in the laminar region. For suppose 5 it may be different. For turbulent flow, it may be different. Now, again, classification of convective heat transfer. Now, actually, the convective heat transfer can be classified based on the nature of the flow. If the flow is caused by the external means like a blower or fan, heat transfer is called the forced convection. Forced convection can again classified in the terms of two: internal flow or it is external flow, such as flow external. If the flow is generated by the buoyancy forces which arises due to the difference in temperature, that is caused by the temperature differences, and resultant mode of convective heat transfer is called the natural convection. And a good example of the natural convection is the cooling of the electron inside a handheld device. Now, and sometimes the combined mode of convective heat transfer is also there. That is the combination of the forced convection, which is commonly known as the mixed convection. Now you can see, suppose the material heated, we have some heating element here. If we are using fan, then the is will be very heated very quickly because and this is an example of forced convection. Suppose we have a table, and if we want to, if we air and we are heat is actually we have the velocity to the heat. So this is an example of natural convection. What happens? There will be no fan because of the temperature difference. The due to the density variation, or that is arises due to the temperature difference, it is goes up in case of the natural convection, and the heat is necessarily the heat from the lake. Okay, so next we can this is same thing, the classification of the convective heat transfer is actually the function of the number. Now, Grashof number is actually plays a very vital role. It is the actually ratio between the buoyancy and the viscous force. Now, in case of the forced convection, you can see the Grashof number is replaced by the Reynolds number and the number. This number is the same role, but differently in the free convection and the forced convection. And you can see that this thing represents Nusselt, Grashof, and the Prandtl number. And Prandtl number is generally a number which actually give us the ratio between the kinematic viscosity to the thermal diffusivity. Now, these are actually in case of the forced and the free convection. But for a mixed convection problem, identification of the flow is very important. How we can identify a mixed convection problem? So that is actually based on Grashof number and the Reynolds number, and that is given by and the Reynolds number from the giving and from the given condition. If you can find that 0.1, that means the buoyancy is unimportant there. So we need not to go for the natural convection, and we can neglect the natural convection. Now, in case of the forced convection, whenever the number by Reynolds, so we can use that for now. Number is visible whenever this number is in between 1 and by Reynolds number square is distinct parameter for mixed convection studies. Next we'll start the introduction to the extended surface or phase. Now the convection heat transfer. So it is very important that convection heat transfer between a hot solid surface and colder fluid is governed by the Newton's law of cooling, that we know. That we already have this H by Ts and infinity, where this H is the convection heat transfer coefficient, hot surface temperature, T infinity fluid temperature. Now, if you want to increase the heat transfer rate, now if you want to increase the heat transfer rate or the heat transfer to convection, that we have the three options. Those three options are either we need to increase the temperature difference between the surface and fluid is Ts minus infinity, or we need to increase the heat space, or we have to increase the area. Now see, it is very expensive actually increase the heat transfer coefficient. And if you use by enhancing the fluid flow or flow velocity, or we need a fan or a blower which makes the process very much, that means expenditure will be more. And similarly, we cannot actually fix the temperature in real situations. With the temperature difference is very much difficult task. So people have not gone for those things. Instead, going there, we are just using the factors. By increasing this area, we can increase the heat transfer. So increase the area of contact or exposure between the surface and the fluid. That will the basics of the starting of the extended surface or the fins. Now by using the extended surface or the fins, we can increase the area, which in turn increase the heat transfer rate. Okay. Now next part, this is actually extended meaning for introducing the heat between the surface and the surrounding fluid by increasing the heat transfer. Now this is the bare surface. Bare surface, there is no extended surface. Now if you want to increase the heat transfer by adding the fin, that means we have to increasing this. We are adding these fins here, and it is extended, and this is the protruding part from this base. So that this is the bare surface and this is the fin surface. Now applications or examples of surfaces where actually the fins can be used. Now you can say the advancement of the technology demands the high performance heat transfer devices to extend the life of the heat transfer equipment or to carry away the heat more effectively or efficiently. There exist several applications of heat transfer devices used in industrial, transportation, space heating and radiators, thermal power plants, and many more, in which the higher performance of heat transfer is required. Again, engineering system with a higher performance heat transfer corresponding of increasing smaller weights, smaller volumes, and lower costs are the primary focus of the industry. It is highly essential to find better approach to transport heat from heat exchanger more effectively, which actually this motivates the researchers to look for the better solution. And fins are used to serve such purposes. Now, air-cooled IC engines are some kind of the applications. We can tell about air-cooled IC engines. Then we can say about the refrigeration and condenser tubes, electric transformers, reciprocating air compressors, semiconductor devices, automobile radiators, electronic cooling, computer CPU heatings, reactors, nuclear power plants, solar cells, heat exchangers in the thermal power plants, etc. These are a few examples that I'm collecting from the internet. I see where actually the fins always have to be added in the part where actually the heat transfer coefficient is low. Now, suppose if you consider the IC engine, the gases inside the cylinder and the air at the outside. Now we do to increasing the area means in order to increase the heat transfer coefficient, sorry, we have to add the fins where the heat transfer coefficient is low. So the air side, the heat transfer coefficient is low. That's why we're adding this outside, or that means not in the gas side, it is outside. Exposure to the air. Okay. Similarly, we can say flat plates are rarely used in case of the condenser tubes. Similarly, radiator also, and electric transformer. And you can see this is actually motherboard of a CPU. So where you can see how the heat sinks are used. So So these are heat sinks are nothing but the extended surface. Similarly, in case of the air compressors also, protruding parts are there. These are fins. In almost all engineering applications where actually we need to remove the heat rapidly, so we have to use the fin for the extended surface. Fins can be broadly classified as a longitudinal fin, radial fin, and a pin fin. Now, longitudinal fin, A, B, C, D, that means A, B, and C, and D. These are longitudinal fin with rectangular profile, and this is also a rectangular plate in the oriented radially, but it is considering under the rectangular profile or longitudinal fin only. Now, longitudinal fin and the trapezoidal profile, longitudinal fin with concave parabolic. Similarly, the radial fins are also there in the E and F. These radial fins are also known as the disc fin or the annular fin, or rectangular profiles are also there, and triangular profile is there for this also. And these are the pin fins. So pin fins are generally cylindrical type and tapered profile and the concave parabolic type. The analysis of surface. Now, different approaches the analysis of the extended surface. One is analytical method, another is numerical method, and the experimental method. Now, in case of the analytical method, we have to actually consider some assumptions. So those assumptions are listed here, and those are actually the fin material is homogeneous and isotropic. Now, what is homogeneous? The homogeneous means the properties of the material does not change with respect to the location. It is at anywhere of that material, the property will be same. And isotropic means the properties are same in all directions. So the temperature, again, the second assumption is that the temperature at any cross section of the fin is uniform. That is T equal to Tx only. That means the temperature at any cross section of the fin, that it is not actually changing. The temperature is not changing with respect to the location. Now, again, I will come back to this point that heat transfer coefficient H is uniform over the entire surface. Then again, there is no heat generation. Contact thermal resistance is negligible. Heat conduction is steady state. Thermal condition at the tip of the fin to be non-variant in z direction, and one-dimensional heat conduction exists. Now, the point number 3 here, it is said that the heat transfer coefficient H is uniform over the entire surface. And in the analytical method, this is one basic information, or this is a very basic assumption, that in the analytical studies always people have considered that heat transfer coefficient is uniform over the entire surface. Now, but in case of numerical studies, but in practical experiments, it is not like that, because heat transfer coefficient will be the outcome of numerical studies. Okay, so sometimes because of this, the heat transfer, assuming it is a constant over the entire surface, the analytical results are inferior to the numerical analysis. But sometimes it is better in few conditions, but not always. But most of the times, they have assumed that heat transfer is almost constant over the entire surface. But in numerical studies, that it is the outcome. That means we are calculating the heat transfer coefficient. Okay. Again, this is a very basic information in all kind of heat transfer books. Now, I am just giving a short description of this. So, how to extend surface analytically? So, for this region, suppose we have a pin and a base surface, and we have a rectangular fin is here. So, in the solid part, always we have to consider the conduction, and we are just elemental area of a strip, rectangular strip. We are considering the dx is the thickness of that strip, and we can say that the qx amount of is under here, and qx plus dx is leaving that element. Now, with this, the solid part from solid part to the fluid part, the conduction is happening. So you can say Sc and dx. This is equation number 6. This is from the forest here. It is same. There is no heat. There will be no heat generation, and in the other part, it will be the delta dx. Similarly, Q convection will be A convective T minus P. T is the temperature, the differential element. area of contact, the area of the contact, convective area we can consider as the perimeter of the fin into the length of the L. Now if you assume steady state condition, that means change the time, and writing the energy balance equation for the element, then heat conductivity equal to heat conductivity out the plus so Ux is amount of heat conducted to the element, and it is out from the element, and some amount it is conducted to the element. So if you like this equation, actually assume the T minus of T infinity, and the dx, this is the non-dimensional temperature, and finally we are getting one equation, and this is the third point of second order differential equation, whose general equation can be written by this equation, where C1 and C2 are the constants of integration that are to be obtained from the conditions. Now we can see that whenever this temperature profile, if you solve this problem, we are getting, suppose this is the pin here, and the temperature is varying, the wall is high, is the wall can be high, and so this way it is decreasing. Now depending on this, per line, you can say that the higher conductivity material of the fin will having the lower slope of the heat transfer line. And to entry, the lesser M1 means the conductivity is high, and the slope of the heat line is so having the lower slope of the heat transfer line. Similarly, we have this H in this equation, and we consider so H is a convective heat transfer, and then P is the perimeter of the cross section, A is the area of cross section, and K is the diameter of the fin. Now, similarly for fin, now this is for rectangular fin. Now for pin fin also, if you consider the other parts is same, only the difference is area and the P will be different. That is the cross sectional area will be changed and the perimeter will be changed. Now boundary condition, the 0 temperature theta value will be there, non-dimensional value that will be by T naught mass of T. Now other boundary condition, that is the tip, three as follows. Now you can say the case one, when the pin is infinitely long. Infinitely long means the x equal to infinity. Then we are non-dimensional value is also going to be 0, and the temperature at the tip of the fin will be so similar that way. If you find, then we can get the equation 12. And for other condition is whenever the fin tip is insulated, the fin tip insulated means the tip, the convection and the conduction will be 0. Now this is why the x equal to L, that means at this point the Fourier's law of heat conduction will be 0. Boundary condition, these two boundary conditions are generally known as the derivative boundary conditions. So and similarly we can, if you, the temperature distribution can be obtained by this, by this, and the resulting heat transfer rate we can obtain like this. These are already available in the all standard heat transfer books. So it will not be a problem for anyone, because we can study from the books also. Now the case 3 is also a similar thing. The fin is finite in length and also possesses heat by convection from its end. However, the heat loss, or it is say that the fin is finite in length, definitely there will be some length, and losses heat by convection the tip is not insulated. In such situation, we have to explain the convection heat transfer to the convection heat transfer. And finally, this is why Fourier's law of heat conduction is equal to the Newton's law of heat of cooling. And at the tip, this conduction will be the convection. Now then the temperature distribution can also be given by this equation. Now heat transfer rate through the fin also given by the equation number 14. But we can see that the instead of in the other cases it is L, here this is LC. The LC is the corrected length. Now for corrected length, LC is defined that the heat transfer from a fin of length LC with insulated tip is equal to heat transfer from the actual fin of length L with a convection at the fin tip. Now, if we are choosing the longitudinal fin or the rectangular fin, for that the LC can be written by L plus T by 2. That this T is actually the thickness of the rectangular fin. Similarly, if it is the pin fin, then it is L plus D by 4. So D is the diameter of the circular fin. Now, if we are considering of the fin efficiency, so it is defined as the ratio of the actual heat transfer rate taking place through the fin and the maximum possible heat transfer rate that could occur through the fin. That is when the entire fin is at the root temperature or the base temperature. That means also we can find that we can define the fin efficiency like the heat transfer through non-isothermal fin to the heat transfer to the isothermal fin. Now, in case of the efficiency of the long fin, substituting all the values whatever we have in previous slides for insulated, we are getting like this type of equation. Effectiveness, it is defined as the ratio between heat transfer rate with fin and the without fin. That is also known to all. Now, similarly for long fin and the insulated fin, we can add there. But AR is the area of the liquid. Here we are using the AR because without fin, we have to use the area as the AR. AR is the a root equivalent. It is the area at the root equivalent to the cross-sectional area of the fin. Now, when effectiveness is equal to 1, that fin does not affect the heat transfer at all. And whenever the effectiveness is less than 1, fin actually acts as insulation. That is, if thermal conductivity of the fin material is low. Similarly, effectiveness is greater than 1, so heat transfer will be increased. Some case actually, that is why for fin heat transfer, whenever the effectiveness is greater than 2, this is considered as a standard value for use of the fin can be justified then. Okay, so for the note, we can consider that fins are generally used where actually heat transfer coefficient values are relatively low. That is already I have told. Suppose in case of the IC engine, if you are using the extended surface, then we have to add the heat transfer. We have to add the fins on the sides actually the heat transfer coefficient is low. Now, in case of the gas, the heat transfer coefficient is more. So if we add the extended surface within the cylinder, then it won't serve any usefulness. But if we add it into the outside of the cylinder that is exposed to the air, that may be very useful. So, and again, we can say that fin materials should be made of highly conductive materials. And we are considering aluminum is very much preferable because the conductivity is more and emissivity is low. A good fin material is always having a low emissivity and a high thermal conductivity. Now, low emissivity means that is why in many times in the researches have been considered that the radiation heat transfer can be neglected from the fins because of this reason, that because high whatever material is best for the fin conductivity, that material cannot be actually used because emissivity is very low. Okay, so emissivity should be low is a very good property for a fin material. Now, lateral surface area P by A of the fin should be as high as possible, and fins with parabolic and triangular profiles contain less material and are more efficient, requiring minimum weight. The efficiency of most fins used in practice is above 90%. Okay, so next again, now history and the literature of the fins. We can say that the actually or mechanical for heat conduction air-cooled engine in 1920. This is the first published report on. Now, this NACA is actually the National Advisory Committee for Aeronautics. That is actually of the NASA, National Aeronautics and Space Administration. Okay, so in the 1920s, this is the first evidence that we have done on the world extent. Now, the already whatever we have discussed that actually first discovered was given by the K.A. Gardner in 1950, and it was published in the journal. It is published by the ASME, so it is a very popular journal. So, is by Gardner. Again, the heat is parallel plate by friction. Now, whenever we are seeing the parallel plates, this more and analysis are more or less same for the parallel plates and the fins array. So this work also can be considered as a pioneer work for the fin heat transfer. Now again, if you have someone, if you want to search for the available literature sources, then that means how we can actually search for the so guys, and just giving here, because suppose we have to search first the what mode of heat is, or how the heat is actually transferred, whether it is a free convection or a forced convection or a mixed convection. If it is by natural convection, then we need to say that either it is from the vertical fin or the horizontal fin. So we have it's like convection first for the on convection from vertical fin attached to a vertical base, convection from vertical fin attached to a horizontal base, south vertical fin horizontal base, and natural convection from fin horizontal channel, and heat transfer by convection. Similar also, and again heat transfer by mixed convection. This mixed convection from horizontal channel, mixed vertical channel, and mixed convection from shrouded vertical fin array at the vertical base. Now I'm going, actually we can actually formulate the fin problems, or we are just considering a numerical analysis. We're going to consider a numerical analysis of natural convection studies from shrouded vertical fin array and mixed convection studies from shrouded vertical fin array. Two configurations actually. I will show the how to formulate the natural mix and forced convection approach through approach. I will discuss now. So these I consider the two case studies. That is one convection, another is mixed convection. I am choosing the configuration as shrouded vertical fin array. So very very conventional design of fin array. The placing of the shroud, the placing of the shroud actually enhances the induced velocity or the natural convection velocity. So that's it is a very common design, but the design in the right hand side, this is known as the dual height. So in this dual height for the last decade or so, on the various problems on this kind of configuration, and recently and some other part of the world also some variable or dual height array, where it is proved for the physical configuration, the governing parameters, the variable finite or the dual height fin array can improve the results. So I am my role is crowded, but I am considering this configuration. Now, just from in the next slide, I will tell same thing. This is actually the this is why along fin height is constant. So considering this is the fixed height, or this may be the height. Hello, hello. Oh, is it connecting now? No, no, now only. Now from what time? Hello. Okay. Hello.
Good organized.
Kankan, you can start. You can start. Don't stop. You can start. Oh, Pushkin
Okay. Okay. Is it there? Okay. 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 Now you can see from this that this is the variable height, because as as from the is horizon, or is position in the horizontal oriented base. Now from there it is found that this is very much yeah, that improvement of heat transfer can be obtained for variable height fin. So now process is same. So we are for analysis only one process. This convection of one of the flow processes the light field. So here also can be visible along x. This is z, this is length, and base is along x direction, and this is the fin s. This is a fin distance between the two fins. Now the this consider the fin thickness, and the h1 is the variable height fin. This is the constant height fin. From that means these two and that is the now we are just going related we are getting we are using this experiment for code and information from this from we are just cutting the you can say that the mass momentum considering time delay. Okay, that Wi-Fi is connected, actually showing the Wi-Fi is connection here. Okay, you just connect it, phone is connected. So can where I can keep this. Okay, so governing equations, the continuity, mass momentum, and the energy equation can be utilized. So this is continuity equation, and momentum, energy, and fin conduction equation that can be expressed by this following equation. Here actually the same, it is actually generalized form where that this velocities u, v, and w that represents, or instead of theta we can write u, v, w in case of the momentum equations. and we can write the temperature T in case of the fin conduction equation or in case of the energy equation. Similarly, this theta is only the velocity in terms depending on the momentum or the energy equation, and the phi represents the pressure terms in case of the momentum equations, or same phi is the viscous dissipation term in the energy equation. And in the viscous dissipation term is assumed to be 0 because of the very low velocity is considered in the studies, so we can neglect this one. And psi, only the z directional term, the buoyancy term is assumed, and that we are using in the momentum equation, z directional momentum equation. Now Boson ratio approximation invoked in the gravity force term of the momentum equation by using this relation. So in the z directional momentum equation, we have to apply the Boson ratio approximation. Now mathematical formulation, this is actually the various types of bulk temperature, local Nusselt number, and the overall Nusselt number given by these equations, and these we have actually derived for our configuration. Now what are the initial and the boundary conditions? Now main thing is the governing equations. Now parabolic, it is actually parabolic in z direction since diffusion is negligible. So all our governing equations, what I have discussed in the earlier slides, those are actually parabolic in z direction. So actually for parabolic in z direction, we can neglect actually the diffusion is negligible, and that's why actually need inlet condition to be specified before solution proceeds. So we have two cases. One is natural convection, another is mixed convection. Now in case of the natural convection, the inlet streamwise velocity is unknown. So purely driven due to the buoyancy and the pressure defect at the inlet and the outlet is considered to be 0. Now this is quite natural that in case of natural convection, the pressure defect will be 0 across the line. And to estimate the inlet velocity, the problem is solved with a gas inlet velocity. So the particular for the configuration, we have run this problem with some gas velocities, and we are just monitoring the whatever the pressure drop, how the pressure drop looks like. Now whenever the pressure drops is 0 for a certain inlet velocity, that inlet velocity is we are considered it as a correct inlet velocity or the correct naturally induced velocity. Now whenever the pressure defect at the outlet is found to be 0, so whenever the pressure defect at the outlet is found to be 0, then we are considering that velocity is the correct velocity. So many trials we have actually considered, where we have taken. And similarly in case of the mixed convection, we have to first specify the inlet velocity. In the mixed convection, we directly give some velocities, that is for mixed convection itself. Now after that, we have to split the mixed convection velocity by evaluating the pump and fan velocity based on the decoupling method. So those methods I will discuss next. What are the possibilities of and how we can actually separate the induced velocity or the Reynolds number, that is depending on the forced convection velocity, from the mixed convection component. That means we can consider that the mixed convection velocity is actually consists of the forced convection velocity and the natural convection velocity. Now by decoupling method, we can actually find the pump and fan velocity, then we can easily find the induced velocity also. Those I'm going to discuss in the next few slides. Now next, these are the actually boundary conditions, how we have actually considered. Like in the solid boundary, the no slip and the impermeability condition can be implemented at a base up to the fin height. The 0 velocities and the 0 normal gradients of the temperature are assumed at the symmetry plane passing through the fin of fixed height. Similarly, the boundary conditions in the shroud, we are considering it is a solid, impermeable, and adiabatic surface, and the base of the fin is maintained at the temperature of the base surface, and fin tip is considered it is insulated. Now cross stream velocities are assumed 0 at the inlet, while the inlet temperature is assigned. Next, we can say the methods of evaluation of natural convection velocity present in a mixed convection in vertical fin channel. Now there are two types of methods. Now first, one part is we are considering two cases, that is natural and mixed. In the natural, we are just assuming some velocity, giving some velocities, and we are monitoring the pressure curve, whether it is coming or it shows the 0 pressure drop or not. When it is showing the 0 pressure drop, that means that velocity is our induced velocity. This is natural convection velocity. And again, in case of the mixed convection, we are just giving in the inlet the mixed convection velocity itself, and then by by the different methods, we can find out the force convection velocity. And that is I want to tell these methods of evaluation of natural convective velocity present in a mixed convection in vertical fin channel. Now, suppose this is a problem of mixed convection. In mixed convection, we need to find out how much of natural convection component of the velocity and how much of the force convection component velocity is present in case of the mixed convection. In order to find it, we have actually two methods. One method is known as natural convection computational fluid dynamics method, used in the mixed convection computational fluid dynamics analysis under same thermal and geometrical condition. And other is the force convection decouple method, the applying the same pressure drop in force and the mixed convection across the channel. Now, this is the first method in which we are find out that natural convection computational fluid method. We find the first natural convection geometry and impose thermal condition at the base, and this result is considered to be the induced velocity component, and we have to check for the temperature distribution or fin temperature distribution over the fin in case of the natural convection and the mixed convection. If the red line shows the natural convection and the black dotted line are the mixed convection, the fin temperature distribution. Now, if this for a particular configuration, means its fin spacing is like 0.1, this is non-dimensional fin spacing. Similarly, 0.5 variable height fin, clearance 0.10, some particular Reynolds number, some particular mixed convection velocity. If the natural convection fin temperature distribution is not varying much from the mixed convection fin temperature distribution value, then we can consider this method. Okay, and once we are considering the natural convection velocity component is calculated, then we can directly use this formula, because W in force equal to W in mixed minus W in natural. W is equal to W in force plus W in natural. So we are getting W in natural. So let's subtract this value from W in mixed. So W in force we can obtain. This problem is introduced to evaluate the Reynolds number only, because once we are getting the Reynolds number W in force, that means that will be useful in calculating the Reynolds number. And this method is used by the VIA in 2018, particularly in 2019. This is a very new method. Okay. Similarly, the force convection decouple method. What is this force convection decouple method? In this method, from the literature, as I have told, the W in mix is equal to the W in natural plus W in force. Now, Reynolds number is based on the force convection velocity. Now, this is the definition of the Reynolds number. That is why W in force into A is by kinematic viscosity nu. So, for a pure natural convection, if you choose, then what happens? The pure natural convection, the Reynolds number is 0. Reynolds number 0 means this W in force is also 0. So, what happens? W in force 0 means W in mix is equal to W in natural. If you W in force is 0, that is W in mix is equal to the W in natural. Now, in this regard, if Reynolds number is based on the total inlet velocity, now then what happens? Now we are considering that at the initial portion only we are giving the Reynolds number. That means for such pure natural convection, that means Reynolds number will be equal to W in natural into H by nu. Hence, for a pure natural convection also, this Reynolds number shows that its values are not 0, it is greater than 0. Then process becomes complicated or erroneous. So we cannot use, because this process may be erroneous or it is maybe very complicated. So we can go for the pressure drop. We can check the pressure drop in the mixed convection and the force convection, because the pressure drop in the convection is always 0. So for mixed convection problem, the pressure drop in the mixed convection is what happened? It is always equal to the pressure drop in the force convection, as pressure drop in natural convection is 0. So that means for a particular mixed convection problem, there are two pressure drops, and those pressure drops will be equal. That is, one is related with the mixed convection, another is related with the force convection. So to solve mixed convection problem, for a chosen inlet velocity, W in force equal to Reynolds number for a defined set of Reynolds number. That means in case of decouple method, how it works actually. So we have some inlet velocities, and for that inlet velocity, we have some pressure drop, and we are just finding some force convection velocities, and that means at the inlet itself, we are giving those velocities. So like 769, 1208, 1538, 1978. So these runs we have taken for the force convection. That means for force convection analysis, we are considering these values. Now we are getting some pressure drop for this here. That means for force convection also we are getting some pressure drop. Now we know that the pressure drop in mixed convection is equal to the pressure drop in the force convection. Now for which cases, suppose sorry, okay, now you can say, suppose we have 2197, we are considering this is the mixed convection, and we want to find the natural convection component and the force convection component. Then we have to search for 6.35 pressure drop, because for this 6.35 pressure drop, now this 6.35, for this 6.35 pressure drop, in case of the force convection also there will be a velocity for this 6.35. So we have to check for whether this 6.35 lies. It lies between 5.07 and 6. And suppose 6.35 is between these 2 points. So corresponding to this, we have force convection velocity here in between 1530 and 1978. Now by through interpolation, we can find out that W in force using the values of this pressure drop along with this 6.35 in the middle. We can find the through interpolation we can find the W in force. Now this W in force is 1890 and W in natural, we can just, you can use the W in mix minus W in force, and if you subtract this one, that will become 307. Okay, so this is the induced velocity. Induced velocity, this mass of induced velocity is present in 2197 of the velocity component of mix. Okay, and the force convection about 1890. Now if you adding this 1890 and 307, then we are getting 219. Now computational procedure, this given by 1980 is implemented to the pressure velocity coupling, and continuity equation is converted into the pressure equation and solved. Now we are this whatever governing equation we have written, that governing should be there, and like some difference is used in there from combined and the diffusive terms, the power law schemes are also used. Now, method is followed with a sufficient number of outputs is completed whenever the desired accuracy of the variables is obtained between the subsequent iterations. The tri-diagonal matrix algorithm is employed as the equation solver in each iteration, and the under relaxation factors are used suitably to decrease the possibility of the fluctuation in the flow solution. The grids are generally rectangular in shape, are deployed in all 3 directions, that is X, Y, and Z direction. Non-uniform grids are also deployed near the entrance in the streamwise direction, that is Z direction. To capture the sharp change in the development of the boundary layer, we are just giving the, that means non-uniform grids generally deployed in the solid boundary. Now an in-house computational code that is developed in Photon 90 to solve these problems. Now this is an algorithm that is known as a simpler algorithm that is semi-implicit pressure link equation revised, that is taken from the Fatankar 1980, and these are actually the grids. Now the whatever the stream velocities and the pressure and the temperature, we have considered those pressure, temperature, the axial velocities at the very center of the grid, and the cross stream velocities like U and the V, we are considering those velocities at the staggered location, okay. Now this is actually the rectangular grids of variable dimension across XY plane, because this is the solid boundary. Here you can see the non-uniform grids are used here. We are using the non-uniform grids very close to the solid boundary. Non-uniform grids are there, and this is along the XY plane only. So all the numerical results actually required the grid sensitivity test. That's why we have different fin spacing. We have considering 0.1, 0.3, 0.5 for the different three sets of grids has been tested. They're like 14 by 36, 16 by 40, 18 by 46 for 0.1, and likewise we are getting the overall Nusselt numbers. And then we have noticed that for the irrespective of the grid sizes, the values actually varies very nominally, and that's why we are choosing the 16 by 44.1 fin spacing and 20 by 44.3 and 28 by 44.5. Now experimental validation, we have some experimental validation. I have already discussed that they are operating rate and parameters more or less similar to our the range we have considered. So we have noticed that the variation is very less between the experimental and the numerical findings. For you can see for this circle, suppose for this particular fin spacing and a particular height, this is the circle, and for this is actually from the experimental results, and this diamond shape, it is we are getting through the numerical. This is for one set, and other sets are also there. We have consider the criteria as the difference between the surface temperature and the ambient temperature. That is the temperature difference. We have selected for the temperature difference in the along x direction, and then we are finding the heat transfer coefficient. That is means we have considered from the experimental results, we have first considered the heat transfer coefficient for this particular temperature difference. Then you have reproduced the same data by giving the same values in our numerical code. Then we are getting this. Okay, that means the variation is very less. This is for actually the natural convection. The Turner and McManus work has actually it is a very old work and popular work, and it is under the natural convection. And for mixed convection studies, we have compared our results with the Morgan and Incorpora. Now you can see the present work and the Morgan and Incorpora for mixed convection. We have the percentage deviation around the maximum of the 8%, nearly 7.90%. Is very less. Now results and discussion. Now range of governing parameters. We have whatever the parameters we have choosing. Actually, the study is related to some parametric studies. Also, we are just trying to find out some optimum conditions on which the heat transfer can be improved or heat transfer is more. So for that reason, we have varied the heat transfer, whatever the height is there. That height is the fin height, that is constant at 0.0320. And the H1 star here is non-dimensional height, that is 0.5 to 1. That means 50% of this height. Suppose we are considering the 0.3 as a height, that 50% of this height, then we have to consider 70% of the this height, 80% of the this height, 90% of the this height, and 100% of this height. Similarly, for 0.04 and 0.05 also we are considering. Similarly, the length we are choosing for natural convection, I think it is 0.5, and for mixed convection 0.6, or some cases we are considering the 0.6 length. Now fin thickness 1 mm nearly, and this is also considered by the Turner and McManus in their experimental work. So we have also the fin. Fin conductivity considering as a 150 and a 200. Similarly, wall temperature consider we have the 90 and 100 degrees centigrade, and ambient we are considering 20 degrees centigrade. And clearance, that is the distance between the shroud and the fin tip, we have considered varying it from 0 to 0.3. Similarly, fin spacing we are varying from 0.1 to 0.5. Fin conductance parameter, that is we have selected between 52 and 117. And Grashof number, it is varying from 1.91 into 10 to the 5 to 1.01 into 10 to the 6. And this Grashof number is based on this height, because the height is we are considering is the characteristics dimension in order to non-dimensionalize the parameters. Because this S star is 0.1, 0.3, 0.1, 0.3, and 0.5, or 0.1 to 0.5 we are selecting. This S star equal to S by H. Okay, that S equal to S star into H. So that means for non-dimensionalize the parameter, we are considering the height characteristics dimension. And Reynolds number, it is around 200 to 2100. The various thermophysical properties like density, dynamic viscosity, and thermal conductivity of the working media are evaluated in dust inquiry. For presentation purpose, the fluid properties are evaluated at the mean of ambient and basal temperature bounding parameters. Now, the results can be the axial pressure defect under natural convection. As I have told, the pressure drop across the natural convection, any dark, it is actually 0. That means you can see it starts from 0 and ends at 0. Now what happens? Now the non-dimensional axial pressure defect increases first along with the, that means this is the our axial length, and it is increases, and then it attains some peak value, then again it is decreasing. And we can notice one thing, that whenever the non-dimensional variable height fin is 0.5 or it is less than 1, the axial velocity pressure is always more. That means the pressure defect is more whenever the H1 star is less. This actually directly because of the resistance offered by the variable height is very low. That is why the induced velocity is more. Because of the higher induced velocity, the resistance will be lower and the pressure defect will be more. Similarly, here you can see in many cases, suppose small fin spacing, if you are noticing, it is actually decreasing, because if you consider the lower height, like one Grashof number is low, the or we can see here that we are choosing the 3 fin spacing, and we are plotting the induced velocity with this non-dimensional variable height. We can see this induced velocity is gradually decreasing, and for the lower Grashof numbers, for the middle Grashof numbers, it attains some minimum value, then again increases, and for higher Grashof number it is always increasing. And this all because the induced velocity associated with the lower height of the lower variable height of fin is actually more. That is why the induced velocity, you can see here, it is more, the resistance is low. So similarly for the lower Grashof numbers also, we can see the for Grashof number 1.91 into 10, that is related to the 0.0 meter of height, and we can see that induced velocity is always increasing here. And for the higher and the lower Grashof number, middle Grashof number, it almost attains maximum and then goes decreasing. But for the constant height fin or the conventional design, that is H1 star is equal to 1.0, that means it is 100% of the constant height fin, that is always increasing. Now this is induced velocity correlation in order to design this coordination, so that in future the people can design the configuration. And so directly from these relations, we are using the least square method. A useful form of the correlation is attained for induced velocity by including all governing parameters and correlations as follows. And then this correlation is varies within the range of the Grashof number, varies between 1.91 into 10 to the power 5, and it is between 8.84 into 10 to the power 5. Similarly, S star is in between 0.1 and 0.5, and non-dimensional length is between 10 and 16.67. Clearance is in between 0 and 0.30, and non-dimensional height is between 5 and 1. And fin parameter is always 70 to 117. Now, overall heat transfer coefficient under natural convection, that now we can see that we are just considered a conventional design and the dual. You can see for 0.5, whenever the heat transfer, we can see that for varying the fin, whenever it increases, this heat transfer increases and then becomes remain in between 0.3 and 0.5. But whenever height is low, but in terms of heights, we can see whenever we are using H1 star, because this is here, that is for 0.03, and another for 0.03, it is diamond. So diamond is in here, and other part is here. While we are using the conventional design, the heat transfer coefficient is this. And whenever we are using the variable height fin with height 0.03 meter, then the position is here. That means there is much more improvement while we are using the variable height fin or the dual height fin. Similarly, whenever the 0.04 and 0.05, whenever height we are increasing from 0.03 to 0.04 and 0.05, that subsequent improvement is noticed from the use of the variable height fin. And we can say that after 0.3, the 0.5 and the 0.3, that we have very nominal deviation from in the heat transfer coefficient. It is almost same for the higher higher heights like 0.04 and 0.05. So it is preferable to use the 0.3 fin spacing for these conditions, because it will have the accommodate in the same base. It will accommodate very that means less number of fins that will give them. Or if you use with a variable height fin, then material requirement will be less. Okay, and it will enhance the heat transfer. So again, this is total heat transfer analysis under natural convection. We are considering a base length of 0.20 meter within that we are changing different heights up to 0.03 to 0.05 for different fin spacing 0.1 and 0.3. The fin spacing is given here. These all are the dimensional values here. So now number of channels we are giving, and number of fixed fin height and number of variable height. Now you can see the fixed height or the conventional design. This is actually for the conventional design. This is for the dual height fin. Now you can see whenever we are using the dual height fin for the same configuration, same conditions, the improvement is very high. Now for lower heights 0.03, the improvement, because you can live in from with the conventional design we are obtaining it is a 38.14 watt, but when we are using the dual height fin it is around 101.67 watt. Similarly for other cases also, in almost all cases, whenever it is lower fin spacing, all cases we are getting a very appreciable or very much high enhancement in the heat transfer. But in case of the fin spacing that is more than this 0.1, but it is more or less same. The heat transfer enhancement is not so big or not so large, but it is same. If it is same also, then also we can use the 0.3 fin spacing, also variable height fin, that can be used in case of 0.1 as well as 0.3. So we can get them effective results from this fin spacing. But however, it is recommended to use in case of the lower fin spacing, variable height or the dual height fin array can be used with the very compact fin spacing, because that is why, because it can be seen from here. If you see, suppose we have the 0.1 fin spacing and we have the dual height fin array. So now you are using that fin spacing, that we can see these values are here, and for subsequent conventional design will give the values here. But in case of the 0.3, with the conventional and the dual height that will give. So it is better to use the dual height fin array in case of the lower fin spacing or the compact design fin spacing, that the improvement will be mass. Now the overall Nusselt number, same way we can conclude correlated involve governing parameters of the problem by using 154 data points from the computation, and we can get various results. Okay, so correlation coefficient is found to be 0.98. So this correlation will definitely help in the future the designers of the fins or extended service to get the effective design very quickly. By seeing this the results only, or seeing this correlation only, they can actually obtain their desired design. Now W velocity profiles, these are the velocity profiles at the inlet and the outlet. You can see these are the inlet condition, and usually it is at the outlet condition we have noticed at the initially it is starting from the 0 because of no slip condition, then again it is increasing in the output. It is because of the very high viscous resistance in the later part of the fins, and whenever this increases the 0.3 and 0.5 fin spacing, this is for the lower fin spacing. The higher fin spacing, it is actually gradually decreases. Now we have similar way temperature profile for the various sections. We can see for the initial, this is actually the for 0.1 fin spacing. This is for at the inlet condition. The temperature is almost the base temperature, but it is heated up to the 0.8 value in case of the very outlet. Okay, that is at section 12.105. Similarly 0.3 and 0.5 also, but the fully developed values are obtained near the outlet. And at the initial condition, it is just heated up to near base plate. Here it is nearly the base plate temperature it is obtained in case of the very first section or the inlet sections. Now FRE variations, this is related with the resistance. You can see the whenever the H1 star is very less or H1 star, the dual height fin array, the FRE value will always high. This indicates that the lower fin spacing, because for 0.1 it is very high, and this is because of the high resistance offered by this. And whenever the Grashof number is low or Grashof number is changing, the values are also gradually decreasing. Now this is pressure difference correlation. Similar way we have correlated data for the pressure, and this is ISO contours of velocities. The ISO contours of velocities near the inlet, it indicates that constant velocities are almost parallel to the solid surface and increases away from the wall of the cases. And for variable height also, you can see is that this is the exit, this is for actually inlet. In the exit also, the velocity is noted to proximate in the proximity of the variable fin height, because this dotted line are 0.5. This is, you can see that this is 4,000, 4,500. It is because of the relatively more fluid is bypassed through here, because of the variable height design. And these are the three-dimensional figures. You can see that it is almost along the fin, it is constant. The parabolic distribution is obtained, and in the clearance region, this is for actually the very inlet condition, that is 0.4122. Gradually it is developing. Now you can see this is for exit, that is around 12.10, and this is for 0.1 fin spacing, this is for 0.3 fin spacing. And in the clearance region, in case of the 0.1, it is very less. The resistance is less, and that's why the velocity will be actually here more in this region. And similarly, in case of the dual height fin array also, here we have noticed that the resistance is less, that velocity is decreasing. Now evolution of the temperature, that is almost same as the previous I have told in the two-dimensional cases also. This is the design along, it is actually gradually decreasing from here, from the base, and you can see at the exit is opting and getting the base. Here it is almost the base temperature, but it is heated up to the 0.2 in case of the exit. It is for 0.1. Now isotherms very near the inlet, so the piece of non-dimensional temperature is higher at a base, both fin heights for clearance region, and close to the exit. So we can see the temperature wall set the fluid in the certain regions. Now isotherms of the fins, we can see that this solid line is for the constant height fin or a conventional design, while dashed line is for the variable fin. Isotherm indicate that the constant height fin are actually non-isothermal, more non-isothermal than its counterpart variable height. This is because of the lower thermal resistance of variable fin height due to its shorter length. Because it offers a shorter length, the variable fin, it is the more isothermal. So induced velocity in convection, this is, you can see that this induced velocity, whatever the nacelle convection component present in the mixed convection, so we can plot, and it increases with the clearance, and whenever the clearance mode, the resistance will be actually, that is why the induced velocity will increasing in the both cases. We are constant two Gresham numbers, or corresponding to the height 0.03 meter and the 0.04 meter. Now overall heat transfer coefficient also, you can see for the variable height shows for the lower Gresham number also, we can, if you define types of heights we are using, the heat transfer coefficient shows that variable height actually shows a very improved result, or the dual height fin improved result. So these are, we have correlated the data with the Dogan and Sibroglu. We have plotted the other part, the experimental data results are also plotted with this correlation. So it is reasonably good. Now conclusions, we can already say that whatever the induced velocity increases with the decreasing variable fin height for smaller fin spacing, causing the enhanced heat transfer. And we have the mixed convection, these results are obtained. And for scope for the future work, the present work of natural and mixed convection heat transfer from a shrouded vertical variable height fin array can be extended to study for further in future. Experimental investigation we have not done. We can do the experimental investigation, maybe performed to rate the present findings. Natural and mixed convection studies from a shrouded vertical variable height fin array undergoing simultaneously heat and mass transfer may be done numerically as well as experimentally, because we have already done the heat and mass transfer through the conventional design, but we have not tried on the variable height, so it can be done. From the literature, it is found that most of the studies on the fin heat transfer, including the present one, have focused on the conjugate conduction and convection mode of heat transfer. Radiation heat transfer may be implemented along with the other modes of heat transfer to make the study more wide-ranging. Working median may be changed to enhance the range of the application, and second law analysis of vertical shrouded variable height fin array may be made. Now we can add the vortex generator can be placed between the fin spacing, which is known to enhance the heat transfer. The variable height downward facing fin array may be investigated. So with the help of this, if you want, then people can done this through for they can choose this research work in their MTech master degree course, and in case of the PhD also they can select this type of work for the future. Now these are the references. These are the references I have collected, and the publications actually from whatever I have discussed today, that is from the mixed convection part. I have published this International Journal of Thermal Science along with my guide. This is in my PhD work. This I have done. Similarly, International Journal of Thermal Science, and here Applied Thermal Engineering. This is I have published in 2018. This one is in 2019. Okay, one more paper, extended surface, I have published in IGSMT, International Journal of Heat and Mass Transfer. That is a different work, but it is under the nacelle convection. Okay, thank you.
Thank you. Thank you. Thank you.
Thank you. Thank you very much, Sir Dr. Kannan Kishore Pathak, sir, for a fabulous presentation. And I wholeheartedly thank all the participants for attending the webinar positively. And I profusely thank the entire VVC family for organizing this workshop. And dear participants, the feedback will be sent now. So kindly give the feedback and the certificate will be sent later. Thank you. Thank you so much, sir.